Hello, my name is Roy Simpson, and I'm a professor of mathematics at Kissimmee River College in Sacramento, California. This is another proof in my Proof in Differential Calculus, or Proofs in Differential Calculus series. In this proof, we're going to go ahead and show that having the derivative of a function being 0 for all values of x in some open interval implies that f must be constant on that open interval. There's a couple pieces of information we're going to need prior to doing this proof. So let's go ahead and take a look at those. Prerequisite knowledge here. You got to know that differentiability implies continuity. Specifically, being differentiable at a point A implies you have continuity at a point A. Furthermore, you have to be very familiar with the mean value theorem. So we're going to be using that in our proof. If you need to review either of those concepts, I actually have the proofs, I suppose, of both of those concepts in my Proofs in Differential Calculus series. So let's go ahead and begin the proof. And like any good proof, we just start with the assumption here. We're going to go ahead and suppose that not only f prime exists, but it equals 0 for all x in that open interval AB. Well, then we know by our prerequisite knowledge that f must be continuous on that interval. Now we're going to do a little bit of a trick so we can use the mean value theorem here. I'm just going to pick two random points in that interval, open interval A to B. And I'm also going to have the additional requirement that I'm just going to let C be less than D, just for ordering purposes. It's actually not really important in this proof at all to say that, but I think a lot of people logically like there to be an ordering in a process, so it'd be kind of very nice to say, listen, I have a couple points, C has to be less than D. It doesn't really affect the proof if you do not say that, honestly. Since C and D are values, specifically arbitrary values, between A and B inclusive, then we know that f must be continuous on the closed interval CD. Moreover, it's actually differentiable on the open interval CD. And this is because of the fact that f is continuous on the open interval AB, and that closed interval CD happens to be within that open interval. So if f is continuous on the entire interval, it's got to be continuous on a small sub-interval. Moreover, we know that f prime exists for all x in AB, so therefore f must be also differentiable on a smaller open interval. Okay? That is contained within AB. So that's why I can say that. However, these last two conditions, and I'll highlight those conditions so that you can see what I'm talking about. These last two conditions, being differentiable on the open interval and continuous on the closed interval, are exactly what we need to start using the mean value theorem, which basically allows us to say that there's some point in that open interval CD such that the derivative at that point is equal to the slope of the secant line connecting C, f of C to D, f of D. So that's the slope of the secant line of the endpoints of that closed interval C to D. But we happen to know something about every point within the interval. Every point between A and B, which includes all the points between C and D, okay, the derivative of the function at those points has to be 0. So I'm just going to say this equals 0. Well, the only way for a fraction to equal 0 is if that numerator is 0. So I'm going to go ahead and put this implies that f of C minus f of D must equal 0. That's the only way for that fraction to become 0, which totally implies that f of C must equal f of D. No other way around it. Well, remember, we let C and D be arbitrary values. Let me go ahead and highlight that. I'll use a different highlighter here. C and D were arbitrary values. What that means is that they could be any points between A and B. So basically, for every single point between A and B, the function values at those points must be exactly the same. So since C and D were arbitrary, f of x is always constant for all values that I could pick between A and B. Again, because when you pick 2 points, just as we've shown here, f of one point has to be the same as f of the other point. In other words, the function values have to be the same. That totally implies that this is a constant function. That is actually the end of the proof. A very, very short proof. Nice, clean, succinct, all that fun stuff.